And we have another remote presenter, and we will hear from Kerins, from University of Manchester.
Thank you. Let me just share my screen. Okay, great. I hope everyone can see that. Maybe I could do with starting from the start rather than the end. Okay, I'm going to talk about Rosette's Roman survey of the Earth transit zone. This is a white paper that was submitted from the recent call, and I'm speaking on behalf of all the white paper authors. So this is a survey that is optimized for habitable zone planets, and it is optimized for SETI. And so the idea is that this would be the first ever exoplanet survey that is optimized for future SETI follow-up. And I should say at this point that among the co-authors on the white paper is Andrew Simeon, who is the principal investigator for Breakthrough Listen. And Breakthrough Listen has expressed a willingness to follow up on the sample that Roman will be capable of obtaining, and to follow up those targets with the Allen Telescope Array, one of the main Breakthrough Listen assets. So Rosettes would not only be breakthrough for SETI, it would also significantly expand on the number of known habitable zone Earth-sized planets around the most common galactic stars. And so these are the dominant contributors to Eta Earth. Okay. And Roman will be capable of giving us a new calibration of Eta Earth on galactic scales. The survey will also provide systematics control for the Galactic Bulge Time Domain Survey microlensing and transit exoplanet survey datasets. And so I believe it's an important additional component for the science that those surveys will bring. And the detail of this is listed in the white paper, and the QR code in the top left is a link to that paper. Right, so Earth Transit Zone, for those who may not be familiar, this is simply the band centered on the ecliptic plane within which an exoplanet would see Earth transit the sun. So it's a very thin band. It's only 0.53 degrees in width. But it's a band that is a key region for SETI research. Now I'm going to take a small digression, just allow me to take a small digression before returning to Roman. The key idea behind the Earth Transit Zone as a target is basically a motivation from the use of game theory in SETI. And actually SETI is a great example of a two-player, non-communicating, cooperative game. And these kinds of games were explored in The Strategy of Conflict, written by Thomas Schelling, who got a Nobel Prize for his for advancing the field of game theory. And just to as a backdrop to this, we all, in some sense, live under the ideas of Thomas Schelling, because he's credited with devising the doctrine of mutually assured destruction. And he came up with some interesting ideas for other familiar games. So this is an uncooperative game, a game of chicken, cars running headlong towards each other, and the winner is the one who doesn't swerve out the way. Thomas Schelling's strategy for this was basically when you're heading towards the other car, and when they can see you, you should remove your steering wheel from its steering wheel column and just chuck it out the window visibly in front of your opponent. And what you do there is you remove the win strategy option from them. They can either swerve out the way and lose, or they can die. And so you're relying that they are sane in order for you to win. So that's his solution. It sounds pretty far-fetched and crazy, but actually we do see it in action in this day and age from climate protesters. So here in the UK, we have Just Stop Oil. They sometimes glue themselves to busy roads to stop traffic and highlight climate change. And they are basically acting out Thomas Schelling's game of chicken, his strategy for that. And as far as I know, none of them been run over yet, so it seems to work for them. But with SETI, we're interested in a cooperative game. And we're assuming they, whoever they are, want to be found just like we would like to be found. Okay, so there's this idea of two-player cooperation between two non-communicating participants. And the most famous version of that is the strangers meeting in New York. Basically, two strangers are given the challenge of meeting up somewhere in New York City on a particular day. They're not told when or where. They've just got to work out how to do that. And basically, they try and get into the mind of the other in order to try and optimize their strategy. And it sounds impossible, but here's a YouTube video where ABC News actually undertook this with real people. And spoiler alert, they did find each other. So have a look on that YouTube video to see how that works. And basically, the idea here, coming back to SETI, is that we want to essentially play Strangers in New York, but on the galactic scale. And so a few years back, I wrote a paper on mutual detectability, which provides a sort of natural counterpart to the Strangers meeting in New York, but it's a SETI context. And the idea is that communication will be incentivized by information that both sides know about the other, and both know the other knows it about them. And in particular, when we're dealing with transiting planets in the Earth transit zone, we know that both parties reside on habitable zone transiting planets. The intrinsic strength of the signal is something that's known to both, and we know it for both planets. And we know that each side knows that the more the other side looks at them, the more they'll see evidence of their existence. And we also know who observes the strongest signal. And you might argue that that incentivizes that side to perhaps be the first to transmit. So that's the incentive. I'm not going to go through this formula, but the bottom line that this paper puts forward is that we should target habitable zone, Earth-sized planets orbiting subsolar luminosity hosts. And they happen to be the planets that dominate largest to Eta Earth. So there's a good ground scientific reason to target these systems outside of SETI as well. So focusing on Roman, here's how the Roman wide field imager looks within the Earth transit zone. You can see it actually straddles most of the region. And in particular, the white paper looks at placing a wide field at the intersection of the ecliptic and galactic planes. So there we're in the Earth transit zone, and we're also looking in a region where there's a very large number of stars. So that's about 5 degrees away from where the fields would be for the galactic bulge time domain survey. So a little way away, but not too far away. We've undertaken some detailed numerical simulations of the transit yield. And it depends, of course, on the length of the observing season. So we took a sort of lower and upper limit on that, and also the number of seasons. And we looked at a case where we had just 2 out of the 6 seasons, or all 6 out of the 6 to put a single field. And so the haul from that across those different options ranges between about 120 or so planets to around 630. And that's about 5 to 20 times the currently known number of habitable zone planets around K&M type stars. That's a big scientific haul that's really interesting from a demographics point of view, quite apart from the fact that it's optimized for SETI. The other big reason to consider a separated field is that it can really help with the systematics from both microlensing and transit exoplanet searches. So here we're seeing a map of the microlensing rate. The center there shows the total rate. The left-hand plot shows the rate of short duration events below 20 days, which are dominated by events from the bulge. And the right-hand plot shows events of longer duration between 40 and 60 days that are basically dominated by events from the disk. And the Rosette's field you can see on that right-hand plot is most easily seen as the detached field there towards the left. And what we can see is the Rosette's field is basically targeting disk lensing events, whereas the Rosette's the standard galactic bulge time domain survey fields, these are the Penny et al. Configuration. They're largely dominated by the bulge, but also but also also have some contribution from the disk as well. So a Rosette's field would give a good way to disentangle bulge and disk microlensing.
3 minutes.
Okay, thank you. On the transit side, the Rosette's field also provides good systematics control because it is less strongly blended than the galactic bulge time domain survey fields. This means that the transit depth is a more reliable indicator of the actual size of the planet. And therefore, when you translate from radius to mass via a mass radius relation for terrestrial planets, which is pretty well constrained, the mass error you incur will be less for the Rosette's field than for the other standard galactic bulge time domain survey fields. However, the proper motion in the standard GBTDS fields is typically higher between the host and the blend. And so that can allow decontamination of eclipsing binaries a little bit better in those fields. So there are pros and cons here. And basically the differences between the two is purely down to the difference in blending. Our target stars are typically within 4 kiloparsecs. They're not in the bulge. And so we're sampling with just lines of sight that are 5 degrees apart. We're sampling essentially the same population with both of these fields. And the differences in terms of transit reliability or proper motion is all to do with the blending. So the different blending quality is something else that can help us understand the main sample. So in summary, I'm proposing Roman as ideal for finding large numbers of rocky habitable zone planets. We want to target them within the Earth transit zone to give a targeted, optimized SETI follow-up. We have willingness from Breakthrough Listen to deploy the Allen Telescope Array to follow up on those. And Rosettes would provide excellent science on the demographics of rocky habitable zone exoplanets. It would provide good systematics control, both for the microlensing and for the transit samples for the galactic bulge time domain survey. And this is, kind of a novel, high-impact science and high-impact public appeal project. This is something that the public can latch onto, and maybe there won't be the little green men, but even if there isn't, we're going to get some really, really good science out of it. So, and that's the way I think, is a good approach to SETI generally. Okay, I'll stop there. Thank you.
Dave?
Hi, Eamon. It's Dave Bennett. I was wondering if you were worried about, this public engagement also has some potentially negative effects. Namely, there's liable to be people who think it's a very bad idea to be advertising our presence to other alien species. They may be evil, as they are often in the movies. So that could be not so good. Do you have some way to deal with that kind of thing?
Yeah, I mean, it's an excellent point, Dave. And you're right, you're absolutely right. There is a sort of fear factor. And I think we just have to point out that we give off all kinds of techno-signatures, right? So we have city lights, we have infrared signatures from rocket exhausts, we have pollutants, which, a few decades time, we'll be capable of seeing those in the atmospheres of other nearby planets. So these are things we do. We are already emitting, quite apart from our radio signals. And so the public, I think it's a case of letting the public, honesty with the public and saying these signals are there. We haven't yet seen any evidence of Darth Vader and his stormtroopers coming over to us, so we seem to be okay. I think that basically this survey will not endanger anyone any more than this is a passive survey, of course. We're not arguing here to transmit a signal. We're arguing to listen to signals from a SETI-optimized data set. So I think from that point of view, this survey is not something that the public would worry about. But there are, of course, other aspects that I've just highlighted that perhaps should be in the conversation, and people should realize we are emitting all the time out there.
Sure. I was just curious about the Earth transit zone, and if you could give us a sense of how quickly it moves. Of course, the two-way the two-way light travel time to the inner galaxy is 50,000 years, and on sort of 10 to the 5-ish year time scales, the orbits of the planets are processing around at the couple of degree level. So, how wide of a region do you think we should be looking at?
Yeah, it's a great question, and if I can get it up in time, that's where Roman really comes into its own, actually. So basically, the Roman field is large enough that any planets that saw our signal historically in the past and emits a signal such that we just detected today, they will overwhelmingly still be expected to be within the field. So I'm just trying to bring up a figure here where we consider exactly this, the two-way communication index. So basically, on this index, 1 refers to a signal where the two-way travel time is equal to the expected time for which a target would remain in the Earth transit zone, okay, across the width of the transit zone. So basically, these numbers are much less than 1. In other words, they travel, these planets travel a distance which is much less than the width of the Earth transit zone within a timescale that's equal to the two-way communication timescale. And that's the real benefit of this wide Roman field. So Roman succeeds in having infrared sensitivity, which we need to get to these hosts. It has high pixel resolution, which we need to have as decontaminated a transit data set as possible. And the wide field of view tackles exactly this question, that planets we see today would be in the field and would have been in the Earth transit zone historically in the past. In response to seeing the Earth transit, we see the signal today from a planet that's still in that field.
Okay, for the interest of time, let's move on. Thank you, Iman.
Thank you.